Hi everyone. In this video, we are going to see the lectures of design of reinforced concrete. This is lecture 1. In this video, I'll be talking about flexure. So first and foremost thing is that analysis and design of flexural members. Sorry. Assumptions for a limit state of collapse, that is flexure. This is under class 38 of IS 456-2000. So 38.1 states about the assumptions. Design of limit state of collapse in flexure shall be based on the assumptions given below. First assumption, plane sections normal to the axis. So this is the beam and the axis is, this is the axis. So the plane section, this is the plane section. The plane section normal to the axis remain plane even after bending. This is after bending. Maximum strain in concrete at the outermost compression fiber. So this is the outermost compression fiber. So the maximum strain in concrete, maximum strain is 0.0035 in bending. So in axial compression is different. So in bending, maximum strain is 0.0035. The relationship between the compressive stress distribution in concrete and the strain in the concrete. So note down this: stress distribution and strain in concrete may be assumed to be rectangular, trapezoidal, parabolic, or any other shape, which results in prediction of strength in substantial agreement with the results of test. So it is simply they are telling that the stress versus strain. So y-axis is x-axis is strain, y-axis is stress. So the stress versus strain can be parabolic, uh, can be rectangular shape, can be trapezoidal. So any uh, shape which is substantial agreement with the results of the test. An acceptable stress strain curve is given in figure 21 of IS 456. For design purposes, the compressive strength of the concrete in the structure, uh, the cube compressive strength is different. Here the compressive strength of the concrete in the structure, in any structure, for example, a beam, a column, a beam or column or any structure. So in this structure, the compressive strength of the concrete is 67 times the characteristic strength. That means 0.67 FCK. 67 percentage of FCK. That means 0.67 times FCK. Partial safety factor gamma m 1.5 shall be applied in addition to this. Note for stress strain curve in figure 21. So this is the figure 21. So x-axis is strain and y-axis is stress. So the strain, the maximum compressive strain is 0.0035, and here the strain is 0.002. So up to 0.002, the curve is parabolic, and here the stress is constant. Constant in the region between 0.002 and 0.0035. Area of stress block is 0.36 FCK XU. Area of resultant compressive force shall be 0.42 FCK XU. From the extreme fiber in the compression, resultant force acts at exactly 0.42 XU, where FCK is the characteristic compressive strength, XU is the depth of neutral axis. What is in the neutral axis depth? Where the bending stress equal to 0. Here the bending stress equal to 0. The fourth assumption, tensile strength of the concrete is ignored. Why it is ignored? Because the tensile strength shall be completely taken care by the provided reinforcement. The stresses in the reinforcement are derived from the respective stress strain curve for the type of steel used. So what are all the types of steel? Fe 250, Fe 415, Fe 500. These are the types of steel. So for various types of steel, there are different stress strain graphs are available. So for Fe 415 and Fe 400, 500, and there will be a, similar stress strain graph, and for Fe 250 there will be a different stress strain graph. Typical curves are given in figure 23 of IS 456. For design purposes, the partial safety factor of is 1.15. For concrete, the partial safety factor is 1.5, and for steel, the partial safety factor is 1.15. Maximum strain in the tension reinforcement. So we have seen the maximum strain in the compression fiber is 0.0035. In the case of maximum strain in the tension reinforcement in the section at failure shall not be less than Fy by Es plus 0.002. So this is 0.002 is the proof stress, and we assume that what is our objective? Our objective is that steel should yield first. So at any cost, we are forcing the steel to yield first. So that is the reason here 0.002 is added, and also we don't have any definite yield stress for Fe 415 and Fe 500. In that case also we are fixing the yield point uh, before yield point and after yield point. So all the cases. So this is the maximum strain. So this is maximum strain comes after the yield stress. So that's why the Fy by Es divided by partial safety factor plus 0.002 is the strain. Fy equal to characteristic strength. Es is the modulus of elasticity of steel. The limiting values of the depth of neutral axis for different grades of steel based on the assumption of 38.1. That means previously I explained whatever are as follows. So this is the yield stress of steel, that is grade of steel. This is called grade of steel. Grade of steel. So we have grade of concrete also, that I have explained in my mixed design videos in detail. So here the grade of steel is 250, 415 and 500. XU max divided by D values can be, that is XU max divided by D maximum can be 0.53 or 0.48 or 0.46 respectively to Fe yield strength Fe 250, Fe 250, Fe 415 and Fe 500. The expression for obtaining the moments of resistance for rectangular and T sections based on the assumption 38.1 are given in Annex G of IS code. So that Annex code G derivations all we see in the coming slides. Stress strain constitutive relations of concrete. It starts with the characteristic strength, that is FCK, that is cube strength, where FCK is the 28 days characteristic compressive strength of standard 150 by 150 by 150 cubes. So, what is meant by characteristic strength? All these things I explained in the mixed design videos. So you can refer those videos for better clarity. The 28 days characteristic compressive strength FCK had been reduced to 0.67. How it can be reduced? Due to the combined effects. First effect is cube to cylinder conversion, that is 0.8, and size factor, that is 0.85. So if FCK is multiplied with 0.8 into 0.85, that is equal to 0.67 FCK. IS code therefore uses 0.67 FCK. For limit state design, IS 456 uses a partial safety factor for concrete, that is 1.5. Stress strain constitutive relationship of concrete is shown here. Here the y-axis is stress and x-axis is strain actually. The initial portion is parabolic, and the when the stress strain graph reaches the ultimate, so IS code presumes it as constant. So for the strain range less than 0.002, the stress versus strain response is parabolic. For the strain between 0.002 and 0.0035, the rate of change of stress is constant. So here you can see a constant line, and this is parabola. So design compressive stress are computed as 0.67 FCK divided by 1.5, that is 0.447 FCK. So if it is a cube, then the obtained stress is FCK, and if it is a member, then the obtained stress is 0.67 FCK. For design stress, that is design compressive stress, design stress is equal to 0.447 FCK. So here you can see the graphs how it shrinks. Cube compressive strength, then 0.8, cube to cylinder, that is conversion factor is 0.8 FCK. Then using size factor 0.8 to 0.85, that is 0.67 FCK. 0.67 divided by 1.5 is nothing but 0.447 FCK. This is called design compressive stress. Stress strain constitutive relations of concrete. So equation of parabola is nothing but y equal to ax square plus bx plus c. This is the general form of equation of parabola. Here y is uh, uh, compressive stress and x is the strain. We need three boundary conditions to solve the three constants A, B, and C. These are the three constants. So the boundary condition 1, stress equal to 0, strain equal to 0. So in that case, the constant C is equal to 0. The boundary condition number 2, rate of change of stress with respect to strain equal to 0 when the strain is maximum. This is maximum strain. Substitute this condition. First, if we have to find if this is y, then we have to find y dash. Y dash is nothing but it is almost f c dash. So that is equal to 2a epsilon plus b equal to 0. From there, epsilon equal to minus b by 2a, and substituting these conditions, we will get the equation for B in terms of A. So third boundary condition, epsilon is equal to 0.002, where the stress Fc equal to 0.447 FCK. From these two boundary conditions, from this third boundary condition, we get the value of A as a function of uh, A as a function of B, and just solve these two equations. So these are the two equations. If we solve these two equations, we will get um, A equal to minus 0.447 FCK divided by 0.002 whole square, and B equal to 0.447 FCK divided by 0.002. So further, Fc, that means stress, is equal to 0.447 FCK into epsilon divided by 0.002 minus epsilon divided by 0.002 whole square. So this is the stress strain relationship for the strain values up to 0.002. The stress-strain constitutive relations of concrete. The given equation represents the stress-strain relationship of concrete in compression as adopted in IS 456-2000. In this expression, Fc denotes the stress in concrete, in particular strain epsilon. So if you know the strain, you can find the stress. If you know the stress, you can find the strain. So Fc is the characteristic compressive strength obtained from the 150 mm cubes. For strains less than 0.002, the relationship is parabolic, indicating the stress increases non-linearly with the strain up to the peak value. The expression Fc equal to 0.447 FCK epsilon divided by 0.002 minus epsilon divided by 0.002 whole square captures this gradual increase, reaching a maximum value of 0.447 FCK at a strain of 0.002. For strains between 0.002 and 0.0035, stress remains constant, so that I explained in the stress strain graph, forming a rectangular stress block. This simplification reflects the plastic behavior of concrete after it reaches the maximum stress before failure occurs. Overall, this idealized stress strain curve helps in limit state design to compute ultimate strength of reinforced concrete sections under flexure and compression. Now, area and centroid of the parabola. So, the region bounded by a parabolic curve and the x-axis on a Cartesian coordinate system commonly used in calculus or physics problem to find area, centroid, or moment of inertia. So the upper boundary is defined as, so this is the x-axis and this is the y-axis. So upper boundary, so this is the line and this is the parabola. So description about this parabola, this is y equal to kx square. The parabolic equation, y equal to kx square. Symmetric about y-axis, so you can see the symmetry about y-axis, open upwards from the origin. So this is the origin, 0 comma 0, this is the origin. The base of the region rests on the x-axis, so this is the x-axis where y equal to 0 extends horizontally from minus a to plus a. So this is minus a and this is plus a. X equal to minus a and x equal to a. Shape of total width 2a. The maximum height of the parabolic segment occurs at the edges x equal to a, where the height y equal to k a square. So here nothing but we just substitute x equal to a, we get k a square. Area being analyzed is the region enclosed by the curve and the x-axis, which is shaded in green. So this is the green color area. So the area under this curve we are going to find using the simple formula a equal to double integral dx dy. So this is nothing but the area. So here we are using the formula x equal to minus a2 plus a, where y equal to 0 to k into x square. So here y equal to 0 to k into x square is clearly depicted here. So just by substituting y, and you will get the upper limit and lower limit. Actually here it is not 0, here it is uh, sorry, here it is 0. 0 to k a square. So this is 0. So you will get k a square minus 0 into dx. Sorry, here is x square. So you will get k into x square into dx. That is equal to, you will get 2 by 3 k in the a cube. So this is nothing but 2 by 3 base into height. So here you can see there are two portions. This is portion 1 and this is portion 2. So for these two portions, area under the curve is 2 by 3 base. So this is the total base. Total base is x equal to 2a and height is a, k in the a square. Then area under the semi-parabola. So this is the green shaded area. This is called semi-parabola. Only a half portion is there. So very simple. We have area under the previous curve is 2 by 3 in the base in the height. So just divided by 2, we will get the area of this curve. So in other words, for detailed calculation, x equal to 0, y equal to 0 to k square, and here it's nothing but 0 to k x square, and you will get the 1 by 3 base in the height. Here it is 0 to 1 by 3 k in the a cube. So area of the bounding triangle is nothing but y equal to k in the a square. Horizontal distance is, so this is the b and this is h, and this is, you will get k in the a cube. Now, area under the semi-parabola is nothing but area of the parabolic curve. So this is the region. So earlier we have found this region as 1 by 3 b into h, and this region we have to find the area. So what is the formula? Area of the parabolic curve equal to area of the rectangle minus area under the parabola. So this is the area under the parabola. Area under parabola, and this is the whole portion is area of rectangle. This is area of rectangle. So area of rectangle is equal to base into height. Area of under the parabola is 1 by 3 base into height. Just subtract this, you will get 2 by 3 base into height. The centroid formulas are given x bar and y bar equal to integral of x dA divided by integral of dA, and y bar equal to integral of y into dA divided by integral of dA. So in simple, what is meant by centroid? Centroid is the line of action of the force for the respective area. So for a given x-axis and for a given y-axis, so this is the parabola, and your centroids are x bar and y bar. So this is the small strip and small, and this is a small strip. So this is that small strip, and width of the strip is dx, and the height of the strip is equal to height minus k into x square. So what is this height? Height is nothing but the height, and this part is this point, exactly this point is y equal to k into x square. So this total height minus k into x square, you will get the exact point. The equation of the parabola, we can get it. So we have to find the x bar and y bar. So the formula is nothing but uh, x bar equal to my by a, and y bar equal to um, mx by a. Why it is mx and why it is my? So we are finding the moment with respect to y-axis. So this is the y-axis, and you have to use the thumb rule, and your thumb is facing towards this y direction, and here the thumb is facing towards x direction. So these are the x ordinates. The x ordinates are rotating with respect to the y ordinates are rotating with respect to the x axis, and the x ordinates are rotating with respect to the y-axis. That is why we are calling it as mx and my. So here the my formula is nothing but double integration of x into dA. So here the integral y equal to k x square to the distance of h. So this is the point h. This is the point h, and this is the point y equal to k into x square. So y equal to k into x square to h, and x equal to 0 to a, and integral x dy dx, you will get, the first you have to integrate the dy. So if you integrate the dy, it is nothing but y. So y is nothing but h minus k into x square, x into h minus k into x square, integral 0 to a dx, you get h x square divided by 2 minus k into x to the power of 4 divided by 4, 0 to a, you will get the value of h a square divided by 2 minus k a to the power of 4 divided by 4. So just by substituting h equal to k into a square, and we get the my value ka power 4 by 4, just by divided by 2 by 3 k into a cube, that is area of the curve, area area of the semi-parabolic segment is 2 by 3 k into a cube. So you get the uh, centroid x bar is equal to 3a by 8. So a is nothing but the base 3b, that means base divided by 8. So in the case of y bar, uh, y bar is very important for next calculations. So mx equal to double integral of y into dA. Here x equal to 0 to a, and y equal to k x square to h, and into y into dy dx. So here first you have to differentiate this y into dy, that is y square by 2. So just by substitute this, uh, if you integrate this, you will get y square by 2. So just by substitute this h square minus k into x square into dx, and if you substitute h equal to k a square, h square a equal to k square a to the power of 5, and your mx value is 2 by 5 k square a power 5. And as we know, the area equal to 2 by 3 k into a cube. So your final mx value, sorry, a y bar value is equal to 3 by 5 into h. So h is the height. Um, so x bar and y bar values we have calculated. Depth of neutral axis for singly reinforced beams. Figure illustrates strain profile, idealized stress block. So one is strain profile, another one is idealized stress block, used in the ultimate limit state design for a simply supported reinforced concrete beam section according to IA standard. The diagram has three main parts, all aligned with the beam's cross section itself, the strain profile and the stress block. Cross section B, depth D, tension reinforcement, that is center of the tension reinforcement. The neutral axis is located at distance of xu from the extreme compression fiber. Strain profile, which is assumed to be linear, shows a maximum compressive strain in the concrete at the extreme fiber is 0.0035. At the level of steel reinforcement, the strain in the tension steel shall be, that is maximum strain in the tensile steel shall be Fy divided by 1.15 Es plus 0.002. The stress block is an idealized representation of the concrete stress distribution in the compression shown. It shows the maximum stress of 0.447 FCK occurs the uniform depth of 0.43 XU. So these are all the terms you have to remember when you are writing a GATE exam or any competitive exams. These are the points you have to remember. While the remaining depth is 0.57 XU is taken as the parabolic part. Concrete is assumed to carry no tensile stresses, as indicated by the tensile stress being 0 below the neutral axis. The entire model is used to calculate the moment of resistance of the beam. So for a beam, this is the longitudinal direction, and this is the lateral direction, and this is the transverse direction. So usually the major loads are acting towards transverse direction for buildings, bridges, and or major structures. Except retaining walls, there will be a lateral load comes into picture. A major of the structures comes under this category. So this is a transverse deflection, and this is how the strain profile varies. So this is the width of the beam, and D is the depth of the beam, and this is a neutral axis depth. This is a neutral axis where the uh, strain is 0. So here you can see there is no bending strain, neither compressive strain nor tensile strain. So the strain at the neutral axis is 0, where the strain at the top compression fiber is maximum, and the strain at the uh, uh, tension reinforcement, the tensile strain is maximum. So another level is strain at 0.002. So if you know the strain 0.002 and if you know the stress strain 0.0035, you know the stress. So that's how the stress blocks comes into picture. So you know the strain 0.002, you know the strain 0.0035. At neutral axis the stress and strain equal to 0. So this is how the points were fixed and the stress block comes into picture. So this is a beam of simply supported. So this is a hinged end and this is a roller support, and the plane sections remains plane. You could able to see these are the pillar points at various level. The normal strain is measured. How do we measure the normal strain? First, we have to measure the normal deformation. First, we have to find the First, you have to find the normal deformation. From the normal deformation, we have to find the normal strain. And from the normal strain, we have to find the normal stress. Normal stress. So this is how the calculations. So what we can see and what we can measure is the deformation. So for example, deformation may be 1 mm or less than 1 mm. So we use demountable mechanical strain gauge or electrical strain gauge. So we paste sometimes the electrical strain gauges here, here. So where the original length is known and the change in length is measured. So the strain is change in length by original length. We measure the normal strain. So this is how the at various level we have measured the strain, and if we plot the strain before and after bending, it looks like this. It looks like straight line. So that's why we are telling that uh, plane sections normal to the axis remains plane even after bending. So here the strain profile is parabolic up to strain 0.002, and it is rectangular. That is stress block is rectangle between 0.002 and 0.0035. Then estimating moment of resistance. So this graph diagrams I explained in the previous slide. So still I kept here just to give a brief description about the stress block. So this is called stress block. This is stress block. So the total depth is D. That means effective depth is D. So how to find the effective depth? What is in the effective depth? All these things I'll explain in the coming slides, coming lectures. So depth of neutral axis is XU. So you have two portions. One is rectangular portion and another one is parabolic portion. So the area of the stress block, that is 0.447 FCK divided into 0.43 XU. So this height you can see 0.43 XU. So this is the parabolic region, and this is rectangular region, and this is parabolic region. So this portion is 0.5 0.57 XU, and the remaining portion is 0.43 XU. So how did we arrive this 0.3, 0.43 and 0.57 XU? That I will be explaining in the coming slides. So the force acting in the rectangular section is C1 and the force acting in the parabolic section is C2. So 2 by 3 B in the H, we know that is the area of the parabolic section. So this is base in the height is nothing but the um, rectangular section force. So the force is nothing but in stress block, just the volume is nothing but the force. So breadth in the height in the B. B is the width of the beam. So that is the force acting along the longitudinal axis. So here the x-axis is stress and y-axis is nothing but depth. So how do we arrive this forces C1, C2 and T, that I will be explaining in the coming slides. So we know that the strain varies linearly. So we have two portions, that is 0.002 and this is 0.0035, and this is the depth of neutral axis, and you just differentiate these two portions to uh, um, K2XU and this is K1XU. So K1XU. So 0.0035 divided by XU. This is the total length. This is XU. Is equal to 0.002 divided by K2 into XU. So you will get K2 as 0.57, K1 as 0.43, and compressive stress blocks. So this is the stress block. First portion is rectangular and another portion is parabolic. So this is C1 and this is C2. So C1 is nothing but breadth into depth. So this depth is nothing but 0.43 XU and this is nothing but 0.57 XU. So you know the height and this width also you know, that is 0.447 FCK. So 0.447 FCK, C1 is nothing but 0.447 FCK into 0.43 XU into B. So this is B in the H in the B. And 2 by 3 base in the height. So this is height. So in the B. So just volume is nothing but the force. So C1 and C2 we have calculated, and we will get 0.36 FCK. B in the XU is the sum of forces acting on the compression block. Now the question is line of action. Centroid is the line of action where the C1 and the C2 acts. So that is the line of action. So at what height and what depth it acts. So T is nothing but the tensile force. Fy is the yield strength. AST is the area of steel. So Fy AST is the force. So just we multiply it with 0.87, you will get the factored resistance or factored force which can offer by the tension reinforcement. Just use the force equilibrium. This is compressive stress block and this is the tensile stress block. Tensile reinforcement force due to the tensile reinforcement. You will get the value of XU 0.87 FYAST divided by 0.36 FCK B. So XU by D you will get the value equal to 0.87 Fy divided by 0.36 FCK in the PT. So you will nothing but PT is nothing but 100 AST by P in B into D. So now we have to find the line of action of the forces C1 and C2. That combined C1 plus C2 is nothing but the force acting on the stress block. So where it acts. So take moments about the tension steel. So we have to find the centroid. Centroid is nothing but A1 Y1 divided by A2 Y2 divided by A1 plus A2. So A1 is nothing but the rectangular portion, that is that is par this is A2 is nothing but parabolic portion. So y bar you will get the value of 0.58 xu. That means from the bottom. This is the x-axis and this is the y-axis. So your parabola looks like this and the straight line comes like this. And exact line of action is 0.58 xu. From the top it is 0.41 xu, 0.41 or 42 xu. From the bottom it is 0.58 xu. So this is nothing but y bar. So earlier I explained why we have to find y bar. The y bar is nothing but line of action of the force. So now one more gate question is that if the um, this um, compressive stress is 0.447 fck, that is factored compressive strength. So if it is 0.67 fck or zero point 0.6 fck or 0.8 fck, what will be the line of action? Actually, line of action will not change. Here y bar equal to a1 plus a1 y1 plus a2 plus a2 y2 divided by a1 plus a2, and you will get the same value. So here the stress block, if your stress block is if your compressive stress in the stress block is 0.67 fck, the line of action do not changes. It exactly acts at 0.42 from the 42 xu from the compression fiber. So just by substituting these values, you will get the moment of resistance, that is equal to T into D minus 0.42 xu, 0.87 FYST, D minus 0.42 xu. If you equivalently, you can use the uh, compressive force in concrete, that is 0.36 fck B into xu into D minus 0.42 xu. So we are limiting the at any cost, the concrete strain should not exceed 0.0035. So hence the moment is limited to 0.36 xu max by D 1 minus 0.42 xu max by D B into D square fck. So this is how the um, mu by bd square formula, mu limit divided by bd square formula is arrived actually. Now we will see the codal provisions. Annexure G, that is moment of resistance of rectangular and T sections. So for rectangular sections, the depth of neutral axis is nothing but xu by D, that is equal to 0.87 fy ast divided by 0.36 fck B into D, and the moment of resistance mu equal to 0.87 fy ast into D into 1 minus ast fy divided by BD in the FCK. So in simple words, we can write 0.87 Fy AST into D minus XU. Similarly, mu limit is arrived as 0.36 XU max by D, 1 minus 0.42 XU max by D, BD square FCK. This is a moment of resistance. Limiting moment of resistance of the section. So with this, I conclude my lecture, and lecture 2 and 3 will be released soon.